Hi, I'm Noam, and welcome to this STOC 2021 talk on flow time scheduling with uncertain processing time. And this is joint work with Yossi Azar and Stefano Leonardi. So the problem we consider in our paper is the classic scheduling problem in which jobs are released over time to be processed by some machine. Each job queue takes time PQ to complete. That amount of time is called the processing time of Q, or the volume of Q. In online scheduling, the jobs are revealed to the algorithm only upon their release. The algorithm at any point in time chooses the job to process from the pending jobs that are available. The goal of the algorithm is to minimize total flow time. So that's the sum over jobs of the time from the job's release to its completion. That is the time the job was alive in the system. So here's an example for some scheduling instance. So at time 0, 2 jobs arrive, the blue job with a processing time of 2 and the red job with a processing time of 5. The algorithm chooses to work on the red job for 4 units of time, and then a new job is released, that is the green job with a processing time of 2. Now the algorithm chooses to switch to that green job, process it to completion, then return to the red job, finish it, and then start and finish the blue job. Now the cost of the algorithm in this instance is the sum of the lengths of edges shown here. So there's an edge for each job, which goes from the release to the completion time of that job. And so the total cost here is 18. Previous work on this problem goes way back. So a classic result from the 1950s showed that scheduling according to shortest remaining processing time is actually optimal for this problem. That is, it minimizes flow time. However, there's the question of when does the algorithm become aware of the processing times of jobs. So SLPT actually assumes that when a job is released, its processing time becomes available to the algorithm. So the algorithm knows exactly in advance how much time the job is going to take. Now, this is a sort of assumption that if you think about it, almost never is available in practice, right? This sort of information. So if you imagine a job to be some piece of code that you're trying to run on a machine, it's enough for that piece of code to contain, say, some while loop or something, for the processing time of the job to be actually unknown, right? Or at least not exactly known. So this result is like a very good result in the sense that it's optimal, but it does assume this, it does make this assumption that's somewhat uncomfortable. And this assumption actually motivated the line of work on non-clairvoyant algorithms. So in non-clairvoyant algorithms, the processing time of jobs is not known in advance. So the algorithms work on jobs and are only aware only become aware of the processing time of jobs when the jobs are actually complete. So such algorithms achieve theta of log n competitiveness. So n is here the number of jobs. So this is a pretty nice result when the number of jobs is bounded in some way. But if we're looking at a sequence of like an instance that's very, very long, so n is very, very large, unbounded, then competitiveness is also unbounded. And these algorithms also require randomization. However, it does seem like this cost to be paid of unbounded competitiveness when the number of jobs is large is perhaps somewhat unjustified, because it's sort of like we went to the other extreme. So this algorithm, the non-clairvoyant model, actually assumes that we don't know anything about the jobs, that the jobs are like black boxes for us. And this is also an assumption that's perhaps overly strict. It is possible to know some things about some jobs sometime, right? So we can perhaps make some guess as to the size of the job, and perhaps that guess is not way off. And that brings us to robust scheduling. So we would like to get to this middle ground, so utilize somewhat accurate estimates of processing time. Such estimates could be produced by either the user as it inputs the job into the system, or by some set of heuristics, or by some sort of sophisticated machine learning prediction. So these are things that could occur, and competitiveness would naturally depend on whether this prediction is accurate or not. When we expect that if the prediction is completely accurate, we would like to get close to that SRPT optimality. But if the prediction is randomly generated, in no way related to the actual processing time, we would perhaps expect a worse result. Okay, so here is a formal definition of what we're going to discuss. So upon the release of a job, the algorithm is given some estimate p tilde of that job. So p tilde q, where q is the job. And for some distortion parameter mu, a mu-robust algorithm would maintain its competitive ratio even when the processing times are underestimated by a factor of at most mu. Okay, so that means that the actual processing time of a job is at least the estimate that we're given, but at most mu times that estimate. So here are some examples of distortions that may occur in the model where the distortion is mu. Okay, so now naturally the competitive ratio is going to be the function of this distortion mu. Now some questions that you might have about this model are, what about two-sided errors in estimation? So what I just described is one-sided error when where the processing time of a job is actually always underestimated but never overestimated. So what about two-sided errors where underestimation and overestimation are also possible? So the answer to this is that in the algorithms we describe, the algorithm requires knowledge of mu. And when mu is known, when the distortion, either to the underestimation case or to the overestimation case, when those distortions are known, we can actually scale down the estimates for jobs by the maximum factor of overestimation. And this would turn a two-sided error into a one-sided error. Okay, and the other question is, why use maximum error versus, for example, average error? So this distortion this distortion of mu. It could happen in perhaps one or two jobs, but maybe the rest of the jobs are actually quite accurate and they have very low error. So why do we want competitiveness as a function of mu and not, for example, as a function of the average error? The answer to this relates to the nature of flow time. So in flow time, what could happen is once the algorithm reaches a bad state, that bad state could be maintained by the adversary, thus forcing the algorithm to have a bad competitive ratio even when some prefix of the jobs has been the determining factor in that competitive ratio. So for example, what could happen is there could be some very noisy instance in the beginning of time. So this is a very noisy instance in which the jobs arrive with a very large underestimation. And then once the algorithm reaches a bad state at this point, the adversary could release a sequence of very accurate jobs, so fully accurate. The estimate is exactly the processing time, but that very accurate sequence of jobs actually would cause the algorithm to maintain the bad state reached at this point. But now what you can see is that this stream of accurate jobs of unbounded length can actually decrease the average error down to 1, right? So this means that the average error is in fact not a parameter which we may consider in this problem. Now, our existing algorithm is robust in the way I've just described robustness. So we can consider SRPT, so shortest remaining processing time, when the processing time that we consider is the estimate, right? Because we are not aware of the actual processing time, but only the estimate. So if we do this, then the resulting algorithm is not robust and it has unbounded competitiveness even for a very small distortion. So consider, for example, a distortion of 1 plus epsilon. So we think the job's processing time is 1, but it's actually 1 plus epsilon. And now when you are almost done processing this job, okay, you think you're almost done, you've processed it for like 1 minus epsilon prime time, so you think it has epsilon prime remaining processing time, but actually it has epsilon prime plus epsilon, okay? So what this means is that the ratio now between the remaining processing time in reality and the one that you estimate, this is actually unbounded. So now this means that SRPT is not something that we're able to implement when we're not exactly sure what the processing times of jobs are. So one possible thing that you might consider is using shortest initial processing time instead. So just schedule the job with shortest initial processing time. But this is actually not competitive even without distortion. And this could be quite easily seen. Now our results for total flow time are that for every mu, we give an algorithm that's O of mu squared competitive, which is mu robust. So the main point here is that the competitive ratio is some polynomial in the distortion mu. We also consider weighted flow time. So in weighted flow time, each job has some weight, and we would like to minimize the weighted sum of the flow times of jobs. So that's the completion time of the job minus the release time. So here's the same example as before, but now we also have weights for the jobs. And now the cost of the algorithm is simply the weighted sum of the edges lengths. So this is the weighted flow time setting. For weighted flow time, competitive ratios are in the terms of the parameters of the input. There is no constant competitive algorithm which does not depend on the input in some way. So the parameters that we consider that have been considered are the largest to smallest ratio of processing time, so that's P, the longest to shortest job. W is the largest to smallest ratio of weights, so heaviest job over lightest job. And D is the largest to smallest ratio of densities. The density is just the weight over the volume, so another parameter. And the previously known algorithms for this problem are all have polylogarithmic dependency on these parameters, and the best known algorithms have logarithmic dependency. But the thing is that all of this previous work requires exact knowledge of processing time. So this is something that we addressed in our paper. So for every mu, we present mu-robust algorithms with polynomial dependencies on the distortion mu and logarithmic dependencies on the parameters. And specifically, if we restrict our algorithms to a constant distortion, this matches all best known results. So logarithmic dependencies in all three parameters. Now we describe the algorithm for the unweighted case, which is going to be the focus of this talk. And later we're going to talk a bit about how to extend it in order to get to one of our weighted flow time results. So in the unweighted setting, we're going to give jobs the following visualization. So this is the state of a job at some particular point in time. So this job Q is visualized as a rectangle, and the height of the rectangle is 1, and its width is the remaining processing time of the job Q at that time. So you can imagine that as a job becomes processed, it actually shrinks in width until it disappears. So this is the visualization of a job, and you can notice that the area of the job is actually also its remaining processing time, and this will be important later. Now, our robust unweighted algorithm consists of the following. It maintains two bins, a full bin F and a partial bin P. So here the full bin F contains 3 jobs and P contains 4 jobs. Incoming jobs only go to the bin F, while processing only happens in P. And whenever F exceeds P in weight, a job moves from F to P. So if you consider the life cycle of a job, it arrives at F, then at some point it moves to P, then at P it is processed to completion. Now, the way the job release works is as follows. So you have here 2 visualizations of the same state, but this visualization is the real one and this is the estimated one. So since we're looking now at the full bin F, where no job is being processed, the width of jobs, their remaining processing time, is actually their initial processing time. So this is the initial processing time of the job. So this is the real initial processing time of the job. And on the left, you have the estimated processing times. So the left is the only thing that the algorithm is aware of. It doesn't know the real processing times. It only knows the estimates. So upon release, a new job Q enters the top of the full bin F. Then the algorithm identifies all the jobs in F which are definitely shorter than Q. So what's definitely shorter? It means that the estimate for Q and the estimate for that job are separated by a factor of at least mu. This means that Q definitely has more volume than Q prime. And these are the jobs shown here in blue. Now that the algorithm identified those jobs, it's going to perform a rotation. So what's a rotation? Q takes the place of Q3, Q3 takes the place of Q2, Q2 takes the place of Q1, and Q1 takes the place of Q. So this is the rotation. So this was job arrivals. Now for job processing, we use a very simple rule. We process the top job at P at any point in time. So it's this job here. Since jobs enter at the top, as we're going to see, this processing rule is in fact LIFO, last in, first out. And there are other options for how to process things in P, but we're going to stick with LIFO for now. As for job transfer, whenever F has more jobs than P, we simply slide over the top job from F to P. And this might happen due to job release or due to job processing. So either a job is released to F or a job leaves P due to processing. Now on to the weight ratio algorithm. So in the weight ratio algorithm, for the weighted case, we're going to consider also a generalized visualization of a job, which now has a weight which is not necessarily 1. So the height of the job now is its weight, and its width is the remaining processing time divided by the weight. And this maintains that the area of the rectangle is still its remaining processing time in the system. Now, the previously known O log W competitive algorithm, due to Bansal and Damdil, is the following. You round the job weights. When job comes, you round its weight to an integer power of 2. Then you place the job in a bin, according to the job's weight. Then you choose the heaviest bin and you perform SRPT on that bin. And the main idea is, if you run a constant competitive algorithm in each of log W bins for the unweighted case, this gets you this O log W competitiveness. Of course, it's a bit trickier than that, but that's the main idea here. So here's a visualization of how their algorithm might look. So you have these bins, and in each bin you have the jobs ordered according to remaining processing time. You choose the heaviest bin, and you process the top job from that bin. Now, our problem with this algorithm, for the sake of robustness, is this SRPT component. With estimates, we don't know the remaining processing time, so we can't do this SRPT thing. So our solution would be to replace SRPT, which was an optimal algorithm for the unweighted case, with our robust algorithm for the unweighted case. And so our algorithm looks like this. It has, for each weight class, some pair of bins, a full bin and a partial bin. And we again, when a job comes, we round its way to a power of 2, and we place that job in the full partial bin of its weight class. And at any point in time, we choose the heaviest, i.e. tallest bin pair, and process the top job from its partial bin. So here, it's this bin pair, so we're going to process this job. As for the analysis, I don't have time to go into it, but I will mention the idea behind it, which is to create horizontal bars, such as the bar shown here, and analyze the amount of volume under them. So that's the orange volume shown here. We need to prove that the algorithm flattens volume enough such that the bins are not tall, because the height of the bin is simply the sum of heights of the jobs in that bin, which is the sum of weights, right? So that's the total weight of the bin. If the bins are not tall, this means that these bins are not heavy. And this is used for the sake of analysis. Okay, so to conclude, for unweighted flow time, we present for every mu an O of mu squared competitive, mu robust algorithm. For weighted flow time, we present for every mu algorithms which have polynomial dependency on mu and logarithmic dependency on the various parameters used for weighted flow time. These algorithms match all best previously known competitiveness guarantees, which of course did not allow distortion when our distortion is constant. So we achieve the same bounds as those algorithms, but we also support distortion. When mu is not constant, our dependence, as I said, is polynomial. And now the open problems that occur are that in our results, the algorithms for different values of mu are actually different algorithms. So this means that the way to use our algorithms is to be given mu and then choose the correct alg mu for that distortion, and that alg mu is going to achieve this bound here, which depends on mu. But if we don't know mu, then choosing the incorrect mu could either lead to a lack of competitiveness due to a faulty analysis because we have underestimated the distortion factor, or if we overestimate the distortion factor, we could lose in competitiveness because our algorithm is calibrated for more distortion that is going to occur. A better result would be a single algorithm which simultaneously holds various competitiveness guarantees at varying robustness. So an algorithm alg, which is O of mu squared log W and mu robust for every choice of mu. So it holds those guarantees together. And it seems like for the sake of this issue, we can't use techniques that perhaps would work for other problems. The fact that we don't know mu is not easily resolvable using, for example, doubling techniques. So this another problem that is interesting is finding the best dependence on mu. And we conjecture that the best dependence should be linear. And the third problem is that in the unweighted case, finding the best constant for slight distortions is itself interesting. So if we consider a distortion that's 1 plus epsilon for the unweighted case, then one might think that you can approach something like SRPT, because SRPT is optimal for no distortion. So maybe when the distortion is small, we can approach 1 competitiveness. But in our paper, we show that, in fact, this is not the case. Even for a very small epsilon, a lower bound of 2 competitiveness holds. So it's interesting to find out what the best constant for this problem is. Okay, so thank you, and I hope to see you all at the conference.